Hello, welcome to numerical ship and offshore hydrodynamics. Today is the lecture 48. Today we are going to discussion on the nonlinear time domain panel method. Okay. So, these are the keywords that you have to use to get this lecture. Now, let us jump into the method. Now, here of course, we need to first discuss about the coordinate system. Now, as you know that we are going to all this formulation is based on earth fixed system. Now, in earth fixed system you have a coordinate system which is fixed in earth, and we can call is a at t equal to 0 when there is no wave is a mean location. That means, it is at z equal to 0. And then we have another coordinate system which is o dash, x dash, y dash and z dash, right. This is actually fixed in the body. Now, it is up to you that where you are going to fix your body fixed coordinate system. Somebody placed the origin at the CG location, but here we are putting it at water line just above the CG. So, that means, here it is basically at xg 0 comma 0, in this location actually we are putting our origin. Okay. And then there is a forward speed, and the ship is advancing in a forward speed u, and this S 0 is nothing but the mean weighted surface. That means, at z equal to 0. Now, if you have a I am drawing the 2 dimensional picture like this, right. So, this part we can call is a mean weighted surface. Now, if you consider the wave, then this is called the exact weighted surface, and that we denote as S body. Okay. So, this is about the coordinate system. Now, this is the brief mathematical formulation we have discussed a lot. So, here I am just refreshing you, like here this total potential, total velocity potential, here it is composed of two parameters. One is wave incident phi I, and another we can call, this is called the disturbed potential. Now, under this disturbed potential, as you know, we have that phi steady, then plus phi diffraction, and then plus phi radiation. Okay. So, all this phi, it is included in this phi, fine. Now, here, so therefore, under the assumptions of the linearity, so del square phi t should be equal to 0. So, definitely it is del square phi I plus del square phi equal to 0. Now, as you know that it is under the linearity, again the assumptions is each of the components should be is equal to 0. So, then I can find further split up del square phi I this equal to 0 and del square phi that should be equal to 0, right. So, so this is how actually proceed. The total potential should be 0. So, therefore, del square phi I plus del square phi equal to 0, each of the components should be equal to 0. So, therefore, del square phi equal to 0. Now, this is what we are going to do over here, because the solution for del square phi I is known to me, right, is an analytical solution. So, therefore, we really do not have to worry about del square phi I. However, we have to worry about what about the del square phi. So, all this boundary value problem is based on del square phi equal to 0, right. Okay. Now, here this is the governing differential equation, we know that it is the Laplacian, right, and then together with you have this linearized free surface boundary condition, right, fine. And then we have this body boundary condition. Remember that all are having in the linear. Now, you can ask me that we have the nonlinear time domain framework, that is what we are discussing, that why this all these boundary value problem based on the linearity. We are going to discuss this later on. Now, but however, when we talked about the problem, the major problem, that it is actually linear, what we are going to do is we are going to incorporate some of the nonlinearity in some forces, right. However, the overall structure is linear, and that is what we are talking about, the nonlinearity. If you remember, we discussed in previous classes that it is not purely nonlinear, right. We are again discretizing the several component, and then each several component, some of the component we are considering some part nonlinear. However, the overall framework is linear, and therefore, the solution also in absolutely the boundary conditions are the linear. Okay. Now, this is nothing but V n is nothing but the normal velocity of the body, right. So, and then del phi I del n is nothing but the normal incident potential. Okay. Now, we have already discussed how it is coming, just for sake of completeness, we know that the total del phi, the total potential actually del phi t by del n, that should be is equal to the normal velocity of the body, that is the idea. Now, this total velocity is splitted into two component, one is del phi I by del n plus del phi by del n, that equal to V n, right. And so, therefore, I know that my del phi del n should be V n minus del phi I by del n. So, that is how this formulation has come. Now, under this, how we compute the normal velocity, everybody knows, right. You have to find out V 1, which is the horizontal component of the velocity, you have to find out V 2, we have to find out the V 3, and then of course, that V 4, V 5, V 6, and then you have to find out the V n doing V dot n. Okay. So, this definitely when we are actually some in later stage actually, I am thinking of we are some algorithm again we are going to discuss, that time we will see that how we can do that numerically in computer coding anyway. So, but this is the main equation, which is that is we are going to use to solve for phi or sigma, and then we have the radiation potential and as well as the incident wave potential. So, this is the framework, right. So, and also you know that we have to use these two integral equation are going to solve, right, and this is called the from the you know that idea is the from the source formulation. So, this is the main integral equation, which is the source method, right, and you have the phi equal to, you can solve in terms of a source. Now, here this sigma is unknown to me, and also this phi is also unknown to me, right. We have discussed this before, and then we differentiate this with respect to n, right, and now this is my, now I apply the body boundary condition over here, right, and now here everything is known apart from the value for sigma, right. Now, here we have to find out the sigma, right. Definitely later on when we are going to discuss the algorithm, that you will get to know that it looks little bit I mean you think that this is the expression, this is the unknown that I do in the Wamit type solution. When you do that, this is the unknown, and then right hand side basically a matrix equation, right, and then you are definitely get something about that sigma equal to some kind of influence matrix A inverse into this del phi del n p. If you apply this straight forward, it is actually not like that. Here when you do that, definitely we are going to discuss that how one should do this. Okay. Here I mean, but I just wanted to say only one thing, that here we cannot straightway do that, we cannot do this way, because it is the involvement of this parameter 0 to t. Okay. Now here, because of presence of this, actually this term actually should go into the left hand side, this term should go into the left hand side. Okay. So, therefore, these things actually cannot be the part of the matrix A. Okay. Now, why it is not the part of the matrix A? Why this is the part of this matrix here? That means, actually the sigma is equals to some A inverse, and then this matrix, actually here you have the not only the del phi del n component which is coming from your body boundary condition, also contribution from this also go here, contribution of this also goes here. So, this is, it is not that trivial. We are going to discuss the whole algorithm, okay, at the end of this theoretical session. One or two sessions we devote only to discuss this small algorithm, so that you could able to write this code. Okay. Yeah. So, after this, when you solve this, definitely I get to know what about the phi, right. This phi where we can get. Now, after getting this phi, we need to get the pressure, right. Now, you know that here also again the first part, this first component is my total pressure, right. Now, you can see here it is del phi t by del t plus half grad phi t square and plus z z, right. And definitely this is going to, we are getting this actually in earth fixed system. Now, here I can split this phi t into two component, right. One is phi I and another is the phi. Now, remember that before you apply over here, we have to apply this equation, that del phi del t at earth fixed system should be is equal to del phi del t at body fixed system minus u into del phi del x, right. We have already discussed that when you find out the phi actually we find out in the body fixed reference frame, but my problem is defined on the earth fixed reference frame. So, therefore, we have to change the coordinate system of del phi del t from the body fixed system to the earth fixed system. And once we do that, then everything in a earth fixed system, then only we can apply the whole that phi total, then only you are able to write the total phi t on this earth fixed system. Okay. So, here what we are going to do is as follows. This total phi t, now you know that this is phi t's combination of phi I plus phi, only phi, we can call the phi this term. Now, if we put into here, then actually you can do that by your own, that because you know that what is alpha plus beta whole square, right, all these things you know. So, actually I can get the two component, actually splitted into two component. As I said that when you talk in terms of nonlinearity, we really do not talk about the nonlinear fully. It is some force component, actually we consider some kind of nonlinear thing. Now, what is the component that we are considering in the nonlinear part, that is written in the second pressure expression. So, this total pressure also distributed into two component, one is the linear component and the second one is the non-linear component. Very compressed way definitely I am writing here, but it is your task to break this phi into phi I plus phi and please get these two expression. Now, anything that involves phi, anything that involves phi we solve in linearly. Okay. Now, you see if you look at this expression, now here when you do this del phi t square, that is a plus b whole square. So, a square plus 2 a b plus b square. So, you can see that a b part and then let us say the b square part, it is actually we are here in the linear part. So, because here we have this phi. Now, if you see our the mathematical formulation here, everything we solve in terms of a linear, right, everything is linear, right. So, therefore, wherever we have this phi, definitely it should be in under the assumption of the linearity. So, therefore, wherever I have the phi, any pressure related to that phi we solve it linearly. However, there is another component which is the incident. Now, what is del phi I by del t? It is nothing but the fruit kernel of pressure. So, this is fruit kernel of pressure term, right. Now, when you calculate this fruit kernel of pressure and this pressure I can calculate analytically. Now, when I calculate this analytically, so I can take the exact weighted surface. So, now when we calculate the pressure because of the wave, remember when you do this pressure because of the wave, definitely I can do that with the exact free surface, right. And here also there is one catch, like which surface you call the exact free surface. I am coming here, I am coming here. This concept is really very, when we apply it, it is easy. Easy means we are taking the most simplest situation, but it is very important to visualize the whole aspect and where we are actually compromising and where we are applying the approximation, we have to be very clear about that, right. Now, this line is not at all a very difficult task, right. So, we can for a moment we just skip it right now. Let us focus on when I say that it is the exact free surface, what I mean. Now, what is the meaning of exact free surface? Now, suppose I have I am writing in the 2D only, right. So, we have, let us say I have this ship with me. Now, I have a wave interacting with this ship, okay, and because of that this ship start oscillating, and because this ship start oscillating, then I have the flow everywhere, this side also, everywhere I have a flow. So, initially I have only incident wave potential, we can call this is phi I. Then actually this interaction is with, then this wave is interacted with the ship. When it interacted with the ship, then that waves actually I am getting, it here you have the component of the phi I definitely, but also remember one should not forget that we have the component of phi also, because this body is oscillating, then the wave I am looking at, this wave is superposition of incident wave potential and as well as the disturbed wave potential, which is again the combination of the radiation, the diffraction, the steady everything. Now, my question is, like after some time, like initially everything is fine. Initially I know that there is only phi I. Initially when there is not much interaction, I know everything is coming under the phi I. But after some time, when actually we started that shift started interacting with the wave, when shift started interacting with the wave after let us say some t equal to let us say 10 second later on, then this free surface is not any more with respect to phi I. This free surface is actually combination of the incident wave potential plus the disturbed wave potential. However, the assumptions is that when I say that I am going to find out the Fruit-Kirchhoff pressure on exact free surface, what I mean is I found I am getting it on the exact incident free surface. Again I am ignoring the component of the diffraction force. You are getting it right. Like so that means physically if I look at it, let us say I have this, okay, I have a mobile with me right now, okay. I have this. So, now initially when there is no mobile or no shape, let us say that we have the wave. Now, the moment it start oscillating, then the surrounded wave is not anymore only because of the incident wave, it is because of the ship is oscillating, because of that some component is there. So, that free surface is now complicated free surface, right, but we are not going into that complicated free surface. When you are taking that exact weighted surface, I am taking it on exact incident free surface, because it is easy to find out. Okay. Otherwise, it is not, I am not saying that it is impossible to get the nonlinear free surface, it is easy. I mean it is not that easy, but it is possible, right, because we have the now when we have the expression for phi, I am just telling theoretically how it is possible. When you have this expression for phi, then I can use the kinematic free surface boundary condition and then dynamic free surface boundary condition. If I apply this to free surface condition, then from this phi I get to know what is my eta, that is the wave elevation for the diffracted potential. So, the moment I get eta from the phi, so I know my what is eta, and also I know my eta I, which is a kx cos kx I mean a cos kx minus omega t. I know my eta is something on eta a into cos kx minus omega t, this already I know, and this from eta also I can get this eta also after solving this kinematic free surface condition and dynamic free surface condition. Once I get the solution for phi, right, when I get it from this phi also I can get some eta, I can say eta d eta disturb into some cos kx minus omega t, and if you superpose these two I can get the somehow the exact weighted surface. This is complicated. So, we are avoiding it. So, here when I talked about the nonlinear pressure, this S B is not based on the actual weighted surface, it is the weighted surface under the incident wave potential. So, S B is nothing but the weighted surface under incident wave. Okay. So, this is how we actually get the S B, right, fine. Now, if you understand this one, that how I can obtain the P L, that linear pressure term, and how I can obtain the PNL is basically that. So, what I am getting that I am finding out the pressure at each point. Okay, fine. So, so when I get these two things, so this P linear should be integrated on the weighted surface, the linear weighted surface S 0, and this P in L should be integrated on the non-linear, it is the exact weighted surface under incident wave potential. Both are integration. So, you know that PL PNL is nothing, like you have the panel. Okay, how numerically we do that, we are definitely going to discuss in this algorithm later on, but at least now you should know that how we get the PNL. It is, if this is my ship and if I discretize in the panels, so this pressure should be at the centroid of the each panel. So, that is how we can get the PL. Now, this paneling should be, if it is under the z equal to 0. So, then I can call it is coming over here, and now if you take some this also, I am just making a little bit bolder, and over this we can get it is the on the PNL. Okay. So, now today let us stop at this point, okay, and from next class onwards, how we are try to figure out how to find out this, even if we need to find out this exact non-linear weighted free surface under incident wave, and how to split the panels, right. It is a panel method. So, how to deal with this, all these things we are going to discuss in the next class. Thank you.